invitation to give this talk today. So my talk is about synthesis of non-terminating reactive systems. So in synthesis, you have a specification, which is a relation where one input is in relation with several outputs. And the goal is to synthesize an implementation, which can be seen as an algorithm or a program that selects a unique output for each input. And the input-output combination should satisfy the specification. Yeah, as you've seen here in this little drawing, on the left-hand side, this input can be combined with two different outputs, and an implementation should select one of the two possible valid output combinations for this input. Okay, one very well-known and old synthesis setting is church synthesis. There, the classes of specifications and implementations are very restricted. In this setting, synchronous specifications are considered. I will also call them synchronous relations in this talk. And synchronous specifications can be given by different models. Here, I've used the view of giving them by synchronous transducers with parity acceptance. That means we have an automaton, and on each transition, we read one input letter and produce one output letter. And the acceptance condition is just normal parity. And here in this example, my input alphabet consists of two symbols, not request and request, and my output alphabet consists of two symbols also, grant and not grant. And here, this is a simple specification. It specifies that every request that is made should be eventually granted. So the goal is to stay in this, to infinitely often visit this starting state here, and only finitely often see the state here on the right-hand side. Whenever a request was made, one goes to the state on the right-hand side, and whenever the request is granted, one can come back to the initial state. And yeah, I think most of you have probably seen this kind of request grant specification a bunch of times. And yeah, this is just a simple example to get started. Another view is to not view this as a synchronous transducer, but to consider this as automata, where in each computation step, two symbols are processed, one input and one output symbol, and then one can see a specification as a regular language over a vector alphabet, where in each computation step, one input and one output symbol is consumed. So these are equivalent views. And here in this talk, I choose the view as a synchronous transducer. And then in the church setting, one is also looking for synchronous implementations given by Mealy machines. What are Mealy machines? Mealy machines are deterministic automata, where also for one read input symbol, one output symbol is produced. And it is important that these automata are deterministic on the input component. So the next transition, the target where we go to, is only determined by the input of this transition. Okay, and here you can see this is an implementation of the specification. When the input is not a request, then there's nothing to grant. And if we have as input a request, then we directly grant it. And this is one possible synchronous implementation of the given specification. Okay, and this setting has long known to be decidable. It is decidable whether a synchronous specification is implementable by a Mealy machine. And Mealy machines cover exactly the class of synchronous implementations. But what if we have a relation and it turns out it can't be realized by a Mealy machine? Does that mean all hope is lost? No. We can, of course, consider more powerful models than Mealy machines in order to find specifications. So, and this is the topic of this talk. I want to consider whether we decide whether a synchronous specification is implementable. And here I want to relax the requirement that we want to implement it by a Mealy machine and simply consider, can we implement it in any way? Which means there is an algorithm or a program or some kind of deterministic Turing machine. So this all means the same thing basically, and I will later give a formal definition of what I exactly mean with implementable, but at first let's take a look at some examples. Okay, let's take a look at this specification. It contains pairs of the form A1, A2, A3, and so on. And all input words are in relation with output words, where the beginning of the output word should start with the third letter that we see in the input word. Yeah, this specification is a synchronous specification. It's not difficult to construct a synchronous automaton that recognizes pairs that are in the specification. And here, this is a specification where there is no implementation by a Mealy machine, because a Mealy machine, it reads the first input letter and then it directly has to produce an output letter. And of course, it can't produce the correct letter before it sees the third letter, but it has to directly produce an output letter. So there is no way to have an implementation by a Mealy machine. But of course, it's not difficult to find an implementation. One could simply wait in order to see the third input letter and then, for example, copy the input starting from the third input letter. So this is one of many possible implementations for this specification. So this is a bit more powerful than a Mealy machine. So let's take a look at another example where we have to be even more powerful. Okay, take a look at this. We have a specification. It contains pairs of the form where at first we have a finite string composed of the symbols A and B, and then we wait for a special symbol, big A or big B. And this determines how the output words can look like. Whenever we see a big A in the string, then the output should start. We need as many big A's as we have seen symbols before our special signal A occurred, and the same for B. If we see a big B in the input string, then our output should start with the same number of big B's that we had to wait in order to see the special signal. And then after that, the output can have any form composed of A's and B's. Yeah, this is also a synchronous specification, but now if we want to implement it, the difference to the example before is in the example before, we had to wait until we've seen the third input letter and then could produce output. And here, if we construct an implementation, if we have a deterministic machine, then it has to wait arbitrarily long until it can output something valid. It has to wait until it sees the special signal A or B in order to determine if the output should start with the correct number of A's or with the correct number of B's. Okay, and one of many possible implementations for the specifications is a deterministic machine that computes the following function. UA alpha is mapped to the word AU times, and then the input alpha is copied, and the same for B. If we have a string, then the B and the remainder alpha, then we map it to B U times and copy the remainder of the input. Okay, so here we have seen a specification where the implementation was a bit more complicated. This is an implementation that has to use infinite memory in order to remember how long this beginning of big A.
Sarah, sorry to interrupt. I see a question. So Sanjeeva, you have a question? I see your hand raised. Sanjeeva?
You should allow him to speak.
Yep. Oh,
Thanks. I was just trying to understand the terminology of synchronous, because in what sense are these, is this a synchronous specification? Because if you have to, you don't know how long you have to wait in order to produce the output, then in what sense can you start producing the output? Okay.
It's synchronous in the way that the specification can be specified by a synchronous automata. Like if I go back to the first state, like an automaton that is given here on the left-hand side. For the specification, we see the input and output strings together.
Mhm.
So yeah, it can be specified as a regular language where one input and one output is produced at the same time. So this is what synchronous refers to, that in the specification, the input and output are composed at a synchronous speed.
Thanks.
Yeah, and as said, for the implementation, in order to make this by some kind of deterministic machine, we have to wait until we know whether we have to start with big A or big B. Okay, now I want to formally introduce what it means to be implementable for a relation. It means that there is a computable function f that has the same domain as the relation, and for an input value, the input value and the value assigned by the function, this pair should be in the relation. And this especially means that for all inputs that are not part of the domain, there are no requirements. What happens? Okay, what does it mean for a function to be computable? A function is computable if there exists a deterministic Turing machine that outputs longer and longer prefixes of an acceptable output, while it reads longer and longer prefixes of the input. And I want to go into a bit more detail how such a deterministic Turing machine looks like. Okay. These deterministic Turing machines have three tapes: a one-way read-only input tape, which holds the input word, a two-way working tape, and a one-way write-only output tape. And I have to just introduce some notation. For a Turing machine M of alpha k denotes the output that is written after reading the first k letters of the input sequence alpha. And then we can say that a Turing machine of such a form computes a function f if for all inputs alpha in the domain of the function, we obviously have to have that the output produced by the Turing machine is a prefix of the function value assigned by the function, and that we can produce longer and longer outputs, which is set by the second condition. For every output length I, we have some j, and if we read j letters of the input sequence alpha, then we are guaranteed that the output is at least I letters long. So the machine produces more and more output over time, and the output is a prefix of the function value assigned by the function. So this means for a Turing machine to compute a function f. And now this notion of computability, it is closely related to continuity, to the mathematical notation, which is defined in the usual way with the Cantor distance and convergence. And in the particular case that we have functions from infinite words to infinite words, we can also express it like this. A function is continuous at an input value alpha from the domain if whenever we take words that share longer and longer prefixes with our input alpha, then the function values of these words share also longer and longer prefixes. So that means for every output length I, we can pick some j, such that for all values from the domain, if the prefix of these words is greater or equal to j, then the prefix of the values assigned by the function is greater or equal to I. Yeah, and the function is called continuous if it is continuous at every possible value from its domain. Let's take a look at two examples. This is the function I have given you as a possible implementation for the specification I've shown you earlier. This is continuous. If you take longer and longer two input values that have longer and longer prefixes, then their output also has longer and longer prefixes. So this function is both continuous and computable. And here another example, we take the function where we have input words alpha, and they are just composed of two letters, A and B, and the output can be A to the omega or B to the omega, and this depends on whether the input word contains finitely many alpha or not, if it contains finitely many A or not. If it contains infinitely many A, then the output is A to the omega, and otherwise it's B to the omega. And this function is not continuous because let's say for every two words that share a common prefix, if you take these prefixes and one you concatenate A to the omega to it, and for the other one you concatenate B to the omega to it, then they share a common prefix, but their function values are A to the omega or B to the omega. So these share no prefix. So we can make words that have longer and longer common prefixes, but their outputs are completely different. So we don't have that that the prefixes of the output values grow. Okay. So we have that whenever a function is computable, then it is also continuous, but the converse does not hold. If you take a look at the definition for continuous, we basically say when the inputs share longer and longer prefixes, then the outputs must also share longer and longer prefixes. And the difference to computable function is that for continuous functions, we do not require that it is actually doable by some kind of machine, and computable simply means that we could compute this also. Yeah.
Sarah, there's another question.
Yeah.
So David.
Hi, sorry, I think I must be misunderstanding, but why is your F1 example continuous? Aren't your two example inputs, I mean, UA alpha and UB alpha can have very long shared prefix, but their outputs don't have any common prefix because one of them, the output starts with A's and the other it starts with B's.
Yes. So what I take in this definition, I can only compare outputs from the domain. And so I will compare complete.
Oh, I see. So, yes. No.
Yeah.
Sorry, I don't see. Sorry.
So when you take so
I believe that the crux is that your index I may depend on the input string alpha.
yes.
It's not uniform continuity.
Yeah, exactly.
Oh, I'm sorry. Okay, I now understand. Sorry.
Okay, so yeah, for every input, you can pick a number. For every desired length of the shared output, you can pick a number of how much you have to read from the input.
Another crucial
in order
ingredient is that you don't require anything if you are looking at input strings which are outside of the domain. So
Yes,
this function
exactly.
can never be extended to a continuous function on the total set of all strings.
Yes. Yeah, and this will play an important role later. Yeah. Yeah, thank you. I was a bit confused for a second myself. Yeah. Okay. So let's take a look at the relation between computable and continuity. So often for classes of functions, these notions coincide. What do I mean by that? Every computable function is continuous. And if I take a look at the class of regular functions or rational functions or synchronous functions, then I have that whenever I have a continuous function, this function is also computable. The class of regular functions is a very powerful class of functions. There are many computation models that capture these kind of functions, which are very expressive. Included in this class are rational functions. These are the functions computable by asynchronous transducers. We will later see an example of asynchronous transducers. And inside of rational functions are synchronous functions. These are the functions computable by synchronous transducers. And this is the kind of automaton you have seen on my second slide. And if we consider synchronous functions that are also computable, then this is the class of functions that is computable by Mealy machines. Okay, so that's the relation between computable and continuous functions. And before I present you the results, I want to talk about total and partial domain. Usually in synthesis, there is assumed that the specification has a total domain, and otherwise the synthesis task simply fails. But this view is not very realistic because, for example, you could have an environment where you wait for a special kind of signal in order to do something, like I've shown you in the example before. So this is why in this talk we focus on specifications that have a partial domain. So again, this is the example from before. Here it has the partial domain, a finite number of A's and B, and then this signal big A or big B, and then we can continue with small a or small b. We have seen this can be implemented, and we can see that it makes a difference whether we talk about specifications with total or partial domain. Obviously, total domain sorry, is a special case of partial domain, but if we try to take a specification with partial domain and complete it somehow so that we obtain a specification that has total domain, then it does not preserve the property that the specification remains implementable. If we take a look at this example, we have seen that we can implement it, but if we try to complete the domain, it would also include all input values where the string simply contains only small a and small b. And if we imagine that we have some kind of implementation, then we would read a string, for example, that only consists of small a's. Then eventually we would produce one output symbol, and whatever output symbol is produced, this could be wrong. For example, if a big A is produced, then if in the input a big B occurs, it was wrong. And otherwise, if big B was produced and then in the input at some point a big A occurs, this was also wrong. So here there is no possibility to make this complete and remain implementable. So now I want to show you some results for total domain that were already known. In 2010, it was shown that it is decidable in 2x time whether a continuous function can be synthesized from a given synchronous relation with total domain. And it was later shown that this problem is x time complete. Okay, and now we ask ourselves, when we synthesize a continuous function, is this also a computable function? Because this is what we want. And it turns out, in this case, the synthesized functions are computable, and they are computable by sequential transducers. So what are sequential transducers? Sequential transducers are sequential if their underlying input automaton is a DFA. So let's take first a look at an asynchronous transducer. These are automata that are labeled by pairs of words. One input and one output word. And the output word can be as long as we want to. It can also be epsilon, same for the input. And if it's sequential, it is of this form. If you would project the output component away, then you have DFA. So this means that the target of a relation just depends on the red input symbol and does not depend on the produced output. Yeah, and these kind of automata transducer suffice in order to implement synchronous relations with total domain. Okay, and together with Emmanuel Filio, I studied the problem when we have synchronous relations with partial domain, and there it's also x time complete to decide whether a continuous function can be synthesized from a given synchronous relation with partial domain, and these synthesized continuous functions, they are also computable. Yeah, let me give you a proof idea. So the idea is to view it as a game problem between two players, Adam and Eve, and Adam plays input letters, Eve plays output letters. And since we have partial domain, we care whether the input sequence is in the specification domain. And if so, then the combination of the input and output sequence must be in relation with respect to the specification. And if the input sequence is not in the specification domain, then there is no constraint. Okay. But we have a problem. We have seen in our example where we have to wait for the special symbol big A or big B in order to produce something, that it might be necessary that Eve has to have an unbounded look ahead on her opponent's moves. And this is a problem because our goal is to obtain a finite game arena, which means we can't store the look ahead explicitly. But we can overcome this problem, and the idea is, instead of storing the look ahead she needs explicitly, we store a finite abstraction. Okay, so I have more details, but I think I will skip this slide. Okay, and now the big question. Okay, we know the implementation. We can decide whether we have a computable implementations, but do we need the whole power of deterministic Turing machines in order to have such an implementation? And it turns out we don't need the whole power of deterministic Turing machines in order to compute an implementation. If there is an implementation for a synchronous relation with partial domain, then it suffices to have a deterministic two-way transducer that implements it. Okay, let's take a look at this specification again, where we have to wait for our special symbol A and B. How would a deterministic two-way transducer accomplish this? It would start and read and go to the right until it sees our signal A or B and produce no output while it reads it. Then the transducer would go back to the left to the beginning and also produce no output. Then when it reaches the beginning, it can go right again and produce, depending on whether it saw A or B, produce the letter big A or big B until it reaches in the input the special signal A or B again. And then it can simply copy the input while it goes again to the right. So let's compare total and partial domain implementations. We have seen for total domain that if there is an implementation, sequential transducers with bounded look-ahead suffice. Well, I've told you that sequential transducers suffice, and they only need bounded look-ahead. Why is this? The idea is if we assume that we have an implementation, but arbitrary look-ahead is needed in order to determine the next valid output, then such a machine may wait and wait and wait. So it may wait forever, but this would mean that at some point the output completely stops. But since every input is valid, we would read a valid input sequence, but not produce an infinite output sequence. So this is not a real implementation because, we may wait forever in order to decide what the next output symbol is. So the output stops and we don't have a real implementation. If we consider partial domain, I've shown you that deterministic two-way transducers suffice, sequential transducers do not. If you again think of the example I gave you where we wait for this special signal A or B, then if we have a sequential transducer, it has only finite memory. It can't remember how long it has waited in order to see the signal A or B. So we can't do this with a sequential transducer, and we have to use deterministic two-way transducers, which have infinite memory in the sense that they have access to the whole input, again, by going back to the left or right. And unbounded lookahead may be necessary, for example, in the example I've shown you a bunch of times now. Okay, here's a summary of what we know so far. We took a look at synchronous specifications with total domain and with partial domain, and by implementations by Mealy machines and by computable implementations, and the setting where we have synchronous specifications with total domain and are looking for implementations by Mealy machines. This is the church setting, and it is X-time complete. When you start with a specification given by a non-deterministic automaton. It is also X-time complete if you start if you have a domain that has partial domain. If we are looking for implementations by Mealy machines, the partial domain case can go back to the total domain case. In this setting, it is possible to complete the domain of a partial specification and make a total and preserve implementability by Mealy machines. We have seen if we simply ask for computable implementations, then it is no longer the case that we can go from the partial domain case to the total domain case. For the total domain case, it was already known that it is X-time complete. This result assumes that the specification is given by a deterministic automaton. And this is the same assumption I also make. And then it is also X-time complete. So the complexity does not change in order to determine whether there is an implementation, but the type of implementation changes. For total domain, it suffices to consider sequential transducers, which are finite memory devices. And for partial domain, sequential transducers do not suffice anymore, but we have to go to deterministic two-way transducers. And yeah, they may need to use the feature that they can have an unbounded look-ahead. Okay, so this is the main result I wanted to show you. But now we can ask ourselves, what if we take a look at specifications that are more powerful than synchronous specifications? Could we also decide if there are implementations? Can we compute implementations? Okay, the first step is to take a look at rational relations. These are the relations that are given by asynchronous transducers. Asynchronous transducers are the automata where you read pairs of words in a transition, one input word and one output word, and it turns out it is undecidable whether a given rational relation can be implemented. And yeah, to be more precise, it is undecidable whether a continuous or a computable or a sequential function can be synthesized from a given rational relation. So no matter what you ask yourself, it's basically undecidable. And yeah, for finite words, if you consider rational relations over finite words, there it is also undecidable whether a sequential function can be synthesized. Okay, and the undecidability proof, it is similar to the finite word setting. It is a reduction from post-correspondence problem. Yeah, I will just quickly go over it. Yeah. So we have an instance of the PCP problem. We have the dominoes. The upper halves are labeled with U1 to UN, and the lower halves are labeled with B1 to Bn. And then we have to construct a rational relation. And the rational relation starts with a finite number of indices, which should be the indices of the dominoes. And then, yeah, the remainder ends with an infinite string composed of A's and B's, and the output depends on whether this remainder of A's and B's contains infinitely many A's or not. If it contains infinitely many A's, then we want that our output starts with the corresponding sequence of the upper domino halves of the corresponding U sequence. And if the remainder of the input does not contain infinitely many A's, then we allow every output that does not start with the corresponding B sequence. Okay, and then the idea is if the PCP instance has no solution, then for every sequence of dominoes, the U sequence is never equal to the B sequence. So for an implementation, it is safe to simply output for the integer sequence the corresponding U sequence. It will always satisfy the conditions that whenever we have infinitely many A's, that we have the right U sequence. It will never be equal to the B sequence. So in the other case that we have finitely many A's, it will also be a valid output sequence. Okay, when the PCP instance has no solution, then we can't do an implementation because no deterministic machine can know whether the remainder will have infinitely many A's or not. So we don't know whether to produce the U's or to avoid it. So it's not possible to have an implementation. Okay, then work in progress are deterministic rational relations. This is a class that lies between synchronous and rational relations. It's given by a special kind of transducers. There the state set is partitioned into input and output states, and the transition function is deterministic in the sense that for input states, the one input symbol determines the target state, and for output states, one output symbol determines the next state. Okay, this is a simple example. This automaton already recognizes a function. What does it do? It produces no output and waits for the symbol sharp, and then the output is simply copied. A is copied, B is copied. So it recognizes the function where we wait for the sharp and then copy the remainder of the input. And this is not a synchronous function. So with deterministic rational relations, we can express more than with synchronous functions. For example, we could make relations that use infixes of words and something like that, which is not possible if we restrict ourselves to synchronous specifications. And for these specifications, we obtain the same results. We are mostly sure, like 99%. It is decidable whether a continuous function can be synthesized from a given deterministic rational relation. And these continuous functions are also computable, and it turns out it also suffices to consider deterministic two-way transducers as implementation devices. And the proof techniques that are used for that are the same as in the case of synchronous relations. Okay, I want to stop the talk with one open question. I've shown you that it is decidable whether a synchronous relation with partial domain is implementable, which means we have the ability to use unbounded memory, but it is open if we ask, is it decidable if there is an implementation that uses only finite memory? We know for total domain, asking for an implementation, if there is one, there is always one by a sequential transducer, which is a finite memory device. So for total domain, this question is not open, but for partial domain, we don't know. So for example, if we take a look at this specification, where the input can begin with an arbitrary number of A's, and then we either see B or C, and the output must start with B or with C, then we can implement it by a finite memory device. For example, if the input contains B, then the output is B to the omega. If it contains C, then the output is C to the omega. And of course, this can be done by a device that only uses finite memory, a sequential transducer, for example. Okay, then, these two new results I've shown you, I've added it to the summary table, and this concludes my talk.
Okay, so thank you very much, Sarah. And right, okay, I can already see a question. So Martin, please unmute yourself and go ahead.
Hi, Sarah. Thanks for the interesting talk. I was wondering about the lower bound you have on the complexity of machines implementing the functions you synthesize. You say a two-way transducer is always sufficient, and sometimes you need one. But in your example, you only had two reversals, right? You go read the word, go to the A or B, and then go back to the start, and then read it once more. Can you iterate this example to get an unbounded number of direction reversals?
No, you don't need it. If I go to the slide I skipped, on a number of reversals, but you see every symbol only 3 times, I think.
Oh, so this suffices.
Yeah. Where is? Yeah. If you take a look at this slide, so basically the upper drawing should be the input word, and it's partitioned into lookaheads. And the idea of a winning strategy is that we need 2 lookaheads in order to decide what the output should be for the first lookahead factor.
Okay.
And then we can read another lookahead factor until we have collected enough information so that we can decide what the output is for the next look ahead factor and so on. If I show it from the beginning, so we are here, and then Eve can say, okay, I want more look ahead, more look ahead, until she is ready to make a decision, how she wants to, what kind of output she wants to pick for the previous look ahead factor. She picks some kind of state transformation that gives us the information about the output. And then we start building the next look ahead factor and so on until we have enough output to make the next choice. And this kind of strategy, we can translate it into deterministic two-way transducers that basically work in the same way. The strategy uniquely determines how the factors have to be chosen. And then, yeah, the deterministic two-way transducer reads two factors and then goes back two factors, transforms the first factor, goes forward again, reads another factor, goes back two factors, produces the output matching for the next factor, goes forward two factors, knows what it has to do on the previous factor, goes back.
So that means it reads every letter only 3 times, but it changes between going backwards and forwards infinitely often.
Yes, exactly.
Okay, I see. And do you have an example that shows that this is necessary, that you have to change direction between left and right infinitely often? I would assume you can modify your language you have to play the same game infinitely often.
Yeah, I assume. Would it be still synchronous if I play the same game infinitely often? I guess one could somehow.
Maybe with some padding in between so that you have some time to restart it. I don't know.
It seems possible to play it infinitely often and make it so that the input-output for each game is still exactly underneath each other. Yeah, it seems doable.
Okay, thanks.
Okay, so Peter, can you unmute yourself and ask?
I hope I'm already unmuted.
Yeah, you are.
Okay, I noticed that along your line of argumentation, you use this argument that if there are arbitrary long input sequences where the machine doesn't produce an output, there is also an infinite sequence where it never will produce an output. That's basically Koenig's lemma. So I'm wondering whether you considered a world where this lemma no longer applies. For example, if you go to an infinite input alphabet, take natural numbers as input, then you have your input data becomes an infinitely branching tree and Koenig's lemma no longer applies. So you believe that there is anything provable in that world?
Yeah, actually, on this problem where we consider data words, I started working on it also with Emmanuel Pillot and Nathan Lott and Pierre Laurenier. And yeah, we thought a bit about it, if it still is the case that when we consider specifications with total domain, if it suffices to wait a finite amount of time whenever it is implementable. And it seems that it is still true.
So that means the theory is generalizable to such a setting in some way. Thanks.
Okay, so do we have any more questions?
I have. I just wanted, can I speak?
Yeah, I don't see you. Yeah, I can't see you.
Okay.
Hi, yeah, please go ahead. Yeah.
Yeah, I just wanted to make a comment. About over 40 years ago, I was interested in constructive mathematics. And I noticed, I don't remember all the details now, but I noticed that a lot of the combinatorial movements in this talk and the questions seem to be related to a lot that is being done there. And it's worth to take a look and see whether you can get some ideas from there or immediate results. I think what's going on here is much more fine tuning to what we're doing there. They were doing there. For example, the last question connected with Koenig lemma. I mean, if you look at an function, you want computable functions from real numbers to real numbers, and you want the function to be continuous. You have to, and you look at the epsilon delta definition, then you must decide what the delta after a finite initial sequence of the real number. Otherwise, it won't be continuous. And that immediately reminded me they are doing some things there. They have definitions and so on. But also, I would say, since you have open problems, so don't get too distracted by this. Just see if you can get something out of it.
Yeah, thank you for the tip.
Yeah, well, that's it. That's what I wanted to say.
Okay, thanks. So, more questions? Yeah, David, please go ahead.
I mean, this is probably a kind of trivial question, but it seems like the total v partial distinction is sort of a bit like the distinction of whether you insist that you can say in advance how much progress you'll make for a given amount of input. Are you able to say more precisely kind of what that is?
Yeah, I've not presented results in this talk, but we also studied if we just want to synthesize a uniformly continuous function. And in that case, it also turns out that you only need to wait a finite amount of time when it's implementable.
So that is that kind of saying uniformly continuous is the same as total domain?
Yeah, I think in that case, if it's implementable by a uniformly continuous function, then you could make the domain total and it would also be implementable.
Yeah, thanks.
Okay, so Martin, go ahead.
Yeah, coming back to what you just answered, does that mean you said sometimes you need unbounded look ahead if you have a partial domain? Did I understand the last comment correctly, that means you can also decide whether you can synthesize a function with bounded look ahead? Is this problem decidable?
No, I don't know if it's decidable. I think this relates to the open question whether we can synthesize something with finite memory. So
might be the case that you could do something with bounded look ahead, but still only need finite memory or not. I don't see the connection, but maybe there is some, surely.
if I take a look at, this last example, then I need to have unbounded look ahead, but I don't need to remember everything I've seen. So finite memory suffices. But you are asking if I can decide whether a bounded look ahead suffices, right?
Yeah. Whether there is a function that only needs bounded look ahead. I mean, in the total domain setting, these two things typically coincide. This is one of the results of Holtmann-Kaiser-Thomas.
Exactly. So I would need to find an example of a function which is not uniformly continuous, but still uses only bounded look ahead. So is every function that I can implement with bounded look ahead uniformly continuous? Yes, right?
In the total domain setting, surely I'm not 100% sure about your definition of continuous, but yeah, in the total domain setting, surely.
Yeah. I don't know if this would also be the case for partial domain.
Yeah, this I would have to look at the definition more carefully, whether there's some strange things that happen due to the partial domain.
Yeah, I would have to take a closer look also. Yeah.
There
But
might be something in the introduction of the Holtmann-Kaiser-Thomas paper where they discuss what happens if you look at partial domains. If I remember correctly, there was a short discussion about things that break if you go to a partial domain.
yeah, they
But I'm not
show, I think it contains, if we have total domain, then every continuous function is uniformly continuous. And a counterexample of a
okay.
continuous function which is not uniformly continuous and has partial domain.
Okay, I see. But yeah, it might be an interesting problem, or at least a natural problem, to ask whether it's decidable whether you have a function with bounded look ahead.
Yeah, I agree.
In particular, since they do not coincide in this case. Yeah, I guess.
Okay, so there is a question on the chat. So the question is, is it decidable whether a function implemented by a two-way transducer is implementable by a one-way transducer? And does this relate to your open question in some way? So apparently this participant does not have a microphone, so he's not able to ask it. So I'm asking on his behalf.
Yeah, okay. I don't know if it's decidable. I don't know if someone in the audience knows.
But is it not like the rational function case? Because so one-way transducers typically compute rational functions, isn't it?
Yeah.
So maybe, so but you have an undecidability for the rational functions case.
Yeah, but the question was if I know if
yeah, whether a function implemented by a two-way transducer is implementable by a one-way transducer.
Yeah.
Mm-hmm. Yeah.
I think if we go to finite words, to relations of finite words, then this is decidable.
Mm-hmm.
I think it was some recent result, but I don't know if it's true in the infinite word setting.
Okay. Mm-hmm. Alak, does it answer your question? Do you want to continue on the chat? Okay, so he says it answers the question. So okay, so since we are on the topic of undecidability, I have a question related to this. So you have, so you have shown that rational functions basically that gives undecidability, but deterministic rational functions, which are a subclass, is decidable. Mm-hmm. So okay, so now maybe an orthogonal class could be aperiodic rational functions, which corresponds to aperiodic one-way transducers. Okay. So the reason I'm wondering is, so you already have a result in the finite word case, right? Which you extended to the infinite case for rational functions. So this 2014 result was basically for the finite word case, but rational functions. Is that right? Undecidability?
Yeah, it was not from me, but from Karayol and Döring.
Yeah, sure. Yeah, basically it was known, but it was the rational case for finite words.
Yeah.
And you extended that to the case of to the infinite setting. So I'm just wondering whether this result, the finite setting, do you know if their undecidability requires only this aperiodic rational setting, or do you require non-aperiodic rational?
I'm not sure.
Okay.
I have to.
No, the reason I'm asking is, because at least I think somehow sometimes this BCP encoding may just work even if you are working in an aperiodic setting. So I don't know, maybe if you inspect the proof, it may be clear.
Yeah, I would have to do this, and also you can also do reduction, not from the PCP problem, but there's another more complicated, at least to show it in a slide, from the halting problem of Turing machines. So there would be even two different reductions where I could check what.
Okay, sure.
So the reason why the setting of deterministic rational relation remains decidable is basically when I have an input and an output word, I know exactly what kind of run it will induce in the automaton.
Yeah.
And this property is no longer true if I just go to rational relations. So that is where the proof fails.
Yeah, okay. Yeah, I don't know, maybe worthwhile to see in the periodic setting because again, it's not deterministic. Yeah, but there is a restriction definitely from the full class as well. Okay, so do we have more questions? Looks like there isn't. So let's thank Sarah for a wonderful talk. I request everyone to unmute and so that we can thank her. Okay, so yeah, thank you so much. So thank you, Sarah. That was a wonderful talk. So for the participants, if you wish to stay for the post-coffee break, you're most welcome. And that part is not going to be recorded. Otherwise, we can consider it over.